In this video, we're going to look at heterocyclic aromatics, and we're going to look at a few more advanced problems where aromaticity serves as the root of the answer, or the phenomenon that's at the core of the problem solution. All right, this is Perol right here. Perol is an unusually stable compound. We have not discussed amines in this chapter yet, but as far as amines adjacent to double bonds go, this is an unusually stable compound. And its stability rises from the fact that it's also a 6-pi electron aromatic ring system. We can consider this to be isoelectronic with the cyclopentadienyl anion. Okay. All right, so let me just redraw that here. Okay, so this is totally isoelectronic. The only difference between the cyclopentadienyl anion and Perol is the charge and the identity of the atom that has the negative charge. Okay. All right, so when we do this hybridization change, remember that ammonia is really sp3, but we can turn ammonia to sp2, or we can turn the nitrogen with 3 bonds and a lone pair into sp2. It costs us a little bit in energy, but when this becomes sp2, this lone pair can now overlap with the pi bonds of the carbon-carbon double bonds. And when it does that, you get the 6-pi electron aromatic ring system. Okay, and the fact that you gain aromaticity, which is remember a stability worth more than 100 kilojoules per mole, more than compensates for the fact that this is not the ideal geometry for nitrogen with 3 sigma bonds and a lone pair. All right, contrast that with pyridine. A molecule we've seen before uses a base to quench the HCl that builds up during a tosylation reaction. But here the lone pair is serving a very different function. Okay, so this is pyridine right here. It's more or less it's very similar in structure to benzene. The only difference here is that instead of having a CH here, you have a nitrogen. Pyridine is also aromatic, but for a different reason. And what makes pyridine aromatic is the fact that you have 3 alkene groups, no interruptions in the conjugation, so a completely cyclic conjugated molecule with 6-pi electrons. All right, but what about this lone pair? Shouldn't the lone pair add up to make 8? Well, it doesn't because of where it's located. All right, so when you have nitrogen that's part of a pi bond like this, this means that its lone pair is actually orthogonal. Okay, so this lone pair in an sp2 orbital is not overlapping with the pi system at all, and thus this lone pair here does not count in any contribution to the electrons that we're counting to determine whether a system is aromatic or not. All right, so we can sum it up with a couple of rules here. When the nitrogen has 3 sigma bonds, the lone pair can be part of a delocalized pi system involving adjacent alkene groups. And when the nitrogen is part of a double bond, this functional group right here is something we'll encounter in a few chapters ahead, is called the imine functional group. So an imine type nitrogen, when you have that structure, the lone pair does not contribute to the pi system because it's orthogonal to it, so you do not count this type of lone pair when you're determining whether something is aromatic or not. All right, here's another molecule, furan. Furan has 2 lone pairs at nitrogen. How do we count these? Well, it turns out that furan is also 6-pi electrons and aromatic. And the reason is that we don't count both lone pairs. We cannot cram both lone pairs at the same place at the same time, which is what you'd have to do if you wanted to count all 4 of these electrons as part of the pi system. So you can only count one of the lone pairs. So when you look at the structure for furan, the hybridization here at oxygen is sp2. Again, not the most stable geometry for oxygen with 2 sigma bonds and 2 lone pairs, but by adopting this geometry, you get an aromatic system. 2, 3, 4, 5, 6. 6 pi electrons in a completely delocalized system. So furan, we say, is an aromatic compound. All right. 1 lone pair contributes to the pi system. This lone pair here does, but this lone pair here does not contribute to the pi system. This one counts. These 2 electrons count when you're counting up, does it have 4n plus 2 pi electrons, but this electron, this pair of electrons here does not count. All right, so let's look at some more heterocyclic compounds. This compound here is called imidazole. Notice that imidazole has 2 different nitrogens. This nitrogen right here is like the nitrogen of pyrrole. It's got 3 sigma bonds and a lone pair. So we say that this lone pair here is going to contribute to the pi system. This lone pair here at this nitrogen is, now this is part of a double bond. So this is like the nitrogen in pyridine. And we're going to say that because this nitrogen is part of a double bond, its lone pair is going to be orthogonal to the pi system, and thus it doesn't count. All right, so imidazole is an aromatic compound because we're going to count this lone pair, this double bond, and this carbon-nitrogen pi bond. 2 in the pi bond there, 2 in the pi bond there, and this is where we get our 6 pi electrons. Finally, let's look at this molecule here, oxapine. And oxapine looks like it has 10 electrons, but it not really. Just like furan, we're going to count 2 electrons as being possibly part of the pi system and 2 of the electrons as being possibly not part of, or absolutely not part of the pi system. So when you look at the how many pi electrons are in conjugation in oxapine, there's 2 here, 2 for the pi bond, 2 there, 2 here. So this is 8 pi electrons here, and this one is orthogonal. It doesn't count. Again, just like the second lone pair in furan over there. Okay, so this is an unstable compound. What it does is it actually is in thermal equilibrium with this structure over here called, I guess, benzene monoxide, benzene monoepoxide. Okay. All right, so let's look at a series of compounds. And we're going to write yes if it contains an aromatic ring, and no if it does not contain an aromatic ring. All right, so the first one here, just to give a reference here, I'll just give them letter names: A, B, C, D, E, F, G, and H. All right, so the first one is 1,3,5-hexatriene, and for we know that that's not aromatic. It's not a cyclic compound, so we can't classify that as aromatic. Even though it has 6 pi electrons in conjugation, the conjugation is not completely cyclic all the way around a ring system. So if it's not cyclic, it can't be aromatic in the classic definition. Okay, B, not aromatic. There are 8 pi electrons in conjugation. We'd actually say that B we would call this one actually anti-aromatic. aromatic. It's a destabilized compound. All right, the next one is called azapine. It's also an 8 pi electron system. This lone pair here is on the same type, on a nitrogen with 3 sigma bonds, so it does count in contributing to the pi system. And this one, since it actually has 8 pi electrons in complete cyclic conjugation, we're also going to give the anti-aromatic designation to that one as well. All right, what about D? Well, recall that BH3 is isoelectronic with a carbocation. As an empty p orbital. Okay, so this boron here has 0 electrons in a p orbital. Okay, since we have the p orbital, we now technically have conjugation all the way around the ring system. And since that p orbital has no electrons in it, the electron count comes out to be 6. So we'd have to say yes, that this is in fact an aromatic compound. Okay, cyclobutadiene dication is E. And if we count the electrons here, we need to have complete cyclic conjugation, and we need to have 4n plus 2 pi electrons. Okay, so we have complete cyclic conjugation right here because we have a pi bond there and 2 different p orbitals here since it's carbocation. So we do have the conjugation, and when you add up the electrons, it's 2 here, none there, none there. 2 plus 0 is 2, and 2 is a Huckel number. So yes, there are 2 pi electrons in complete cyclic conjugation. What about F? We're going to turn the dication into the dianion. All right, so we still have complete cyclic conjugation because we have the potential p orbital at every carbon in the ring. We have 2 here, that makes 4 from the carbanions, and then 2 more from the pi bond, so that adds up to be 6. So yes, we have a 6 pi electron system, complete cyclic conjugation. This is an aromatic compound. All right, let's look at G. The thing to note here is that every nitrogen is part of a double bond. So that means that at each of these nitrogens, the lone pair does not contribute or is not overlapping with the pi system. In each one of these, the lone pair is orthogonal. So all we see here is 3 pi bonds in complete cyclic conjugation, a 6 pi electron system. All right, so we're going to say that yes, this is an aromatic system. And in the last one, it's a little hard to see that we have an actual double bond here. But what we see here is that these 2 nitrogens right here are part of a double bond, a nitrogen-nitrogen double bond, but that's a double bond. And this nitrogen here has 3 sigma bonds in a lone pair. Okay, so the lone pair at this nitrogen contributes. The lone pairs at these nitrogens do not, but the pi bond does contribute to the complete cyclic conjugation. So we have 2 from the nitrogen lone pair, 2 from the carbon-carbon pi bond, and 2 from the nitrogen-nitrogen pi bond. And this gives us an aromatic system. Okay? All right, so this is a very common type of problem that you see on exams, predicting whether something will have aromatic stabilization or not based on the number of lone pairs, empty orbitals, and pi bonds that you see in conjugation. All right, here's a very common type of exam question. We're going to look at pyrazole itself and consider which nitrogen of pyrazole is more basic. Okay? And what you would want to think about is, why don't we just go ahead and protonate each of those lone pairs? Okay? That one turns out to be more basic, and this is because when we protonate this nitrogen right here, hydrogen ends up on this nitrogen, and what we end up with is a compound that's still aromatic. 2 pi electrons, or 2 electrons from the nitrogen lone pair there, 2 from the CC pi bond, 2 from the CN pi bond. Okay? When we protonate this nitrogen, there is no aromaticity. We have an interruption in the conjugation. This nitrogen is sp3, and it cannot get out of that. So this system is no longer aromatic. All right. The other thing to note here, the other way to explain this is that this nitrogen is like the nitrogen in pyridine. Okay? This lone pair is orthogonal to the pi system. And we cannot count this lone pair when estimating if this system is aromatic. Okay? But this nitrogen here is essential to making pyrazole an aromatic compound. So this nitrogen is not available to react with a proton. It's busy making the system aromatic. Okay, we're now going to show the product from each of these species. This is just a problem here where you're asked to predict which reaction is more favorable and why is that reaction going to be more favorable. Okay, so we'll call the top reaction A and the bottom reaction B. Here's reaction A, here is reaction B. All right, so let's consider what happens when this undergoes the Diels-Alder reaction. We're going to assume that the Diels-Alder reaction is occurring exclusively at the furan ring and not at the cyclohexadiene ring. All right. So when we do the top Diels-Alder reaction, we actually make a benzene ring. And when we do the bottom Diels-Alder reaction, we don't have any sort of aromatic character at all. So we go from being 10 pi electron aromatic to benzene. And just I think this is something I'm going to mention. This is maybe a concept for a deeper level class than just the first organic chemistry class, but aromaticity. Benzene has a higher degree of aromaticity than heterocyclic aromatic compounds do. Okay, the aromatic stabilization for benzene is much greater. All right, so here in the top one, we go from being weakly aromatic from the heterocyclic aromatic system to a benzene aromatic system. And this is far more favorable than the bottom case where we go from being a weakly aromatic compound to a compound that has no aromatic character whatsoever. So the delta H for the top reaction is more negative, and the reaction occurs at a much faster rate because in the transition state for that process, it's starting to look like a benzene ring. Okay? All right, sorry, I covered that up, so let's just erase that right now. Okay, so let's put the words back up there. Okay, so the top reaction is more favorable. The moderately aromatic furan is converted to the highly aromatic benzene, and the bottom case, the moderately aromatic furan is converted to a ring that has no aromatic character whatsoever. And the bottom reaction, interestingly, is actually a reversible reaction. All right, in this problem, we're going to place the double bonds in the system so as to get a fully aromatic compound, and we're going to predict which compound is likely to be more stable. All right, so in the top one, we get the product that you see here, which we're going to refer, this ring system here is known as isoindole, and this ring system here is known as the indole ring system. All right. Turns out that the bottom system is a lot more stable. This is because we can see two isolated aromatic rings in this compound. But here, our only aromatic ring really is this one, unless you want to consider the larger 10 pi electron system there. Okay, so we actually have benzene type aromaticity in the bottom one, whereas we only have really one aromatic ring system in the top one. So we're going to see that the bottom compound is indole is much lower in energy than isoindole. Okay. All right. Here's another interesting problem. Compound B is a very stable compound. Compound A, called cyclopentadienone, however, was not isolated for the first time until the 1970s and found to be a very unstable compound. All right, so we're going to try to explain that. And we're going to have to look ahead here about something, a structural feature of carbonyl groups, C double bond O's, but they're polarized this way. Even though it's a resonance structure that has one less bond, it's not as good as this one. This resonance structure here explains a lot about the properties of the carbonyl group systems, and we use this resonance form here to explain a lot of the properties. All right, so when we employ that resonance form in A, we get this anti-aromatic compound here. When we employ that resonance interaction in B, we get an aromatic system, the cycloheptatrienol cation, shown here. Okay, so we would say that the natural polarity of the carbonyl group creates an unstable anti-aromatic system in A, while the same polarity leads to an aromatic system in B. Thus, B is more stable. Okay. All right, we're going to do a synthesis problem here. We're going to design a synthetic group to accomplish the following transformation in 5 steps. This one, let's see. What do we know about this synthesis problem here? Throughout this class, only one reaction has been introduced that puts a cyanide group into a molecule, and that's the SN2 reaction of halide or tosylate with Cn-. So that's going to be our last reaction right there. All right. I'm going to use the tosylate because it's a little easier. Tosylates come from alcohols. This alcohol here is the anti-Markovnikov addition product of styrene. Okay, so we could, in theory, take this molecule known as styrene and do the hydroboration oxidation or anti-Markovnikov hydration to produce the compound that you see there. Okay. All right, so our synthesis problem now becomes how to convert this in 2 steps. All right, so we're going to take advantage of the fact that we don't really know a way to introduce to magically steal 2 hydrogens from an alkane, but we can do this in 2 steps. An E2 from that bromide will produce styrene. And that bromide, of course, is the product of halogenation at the benzylic position using NBS and light. An alternative method here, let's see, to do this reaction is to treat this compound with PBr3. and then treat this with NaCN, and that's a perfectly acceptable answer as well. Okay, let's look at this reaction here, and this will kind of serve as a segue into the next chapter. Write a mechanism for the following transformation. We're going to treat this compound with bromine, and is going to produce the bromide there, NHBr, as a byproduct. Okay, so we know that bromine reacts with alkenes. Okay, all right, so this is a reaction from chapter 6. And this is going to give us the 1,2-dibromide. All right. We know that somewhere along the line, the second bromine isn't going to add, but let's just start the reaction off in exactly the same way. All right, so we're going to add bromine. Very likely, we would get the bromonium ion as well. But I'm going to say that we're going to see this probably as our major cationic species, simply because this carbocation here is so well stabilized, it's doubly allylic. So we'll probably see more of this than of the bromonium ion, but there should be an appreciable amount of both species. But this is the species here that's going to allow us to proceed forward. All right, there's a resonance form we can write for any allylic carbocation where we just exchange the position of the alkene group and the carbocation. All right, so we're going to move the double bond here. When it moves away, this leaves a positive charge right there. All right, from this resonance structure, you can now imagine doing a 1,2 alkyl shift. Okay. And this is going to produce this. All right. Bromine could just add to this carbon right here, but a better thing for bromine to do is to do an E1 type reaction, because this actually restores the benzene ring structure, and this is far more favorable. We're not going to see we're not going to see this process here occur to any large extent. Because when you compare the relative stability of this compound and this, there's no comparison, really. This one has a benzene ring. This one does not have a benzene ring. So it's very predictable that this would be the reaction pathway followed and not this reaction pathway down here. Okay. Okay, so I'll draw a better X over the arrow like that. I think this is where this video ends. This serves as the end of the aromaticity chapter. In the next chapter, we're going to actually look at the benzene rings reacting. Okay? All right, so let me advance this. Oh, sorry, we have one more problem. Okay, here. Show the steps in the formation of the indicated products, the naphthalene derivative in CO2 via a Diels-Alder, retro-Diels-Alder sequence. Okay, and we'll look at the thermodynamic driving force in each case. All right, so what we see here in this case is a very favorable Diels-Alder reaction occurring like so. Okay, so this is going to produce a bridge structure, and this produces this compound right here. And this restores the aromaticity in the benzene ring. All right, now what you're going to see happen next is a retro Diels-Alder reaction that's going to give you a second benzene ring. All right, so here we can now have a second Diels-Alder reaction. Okay, and that's going to go like so. And this produces carbon dioxide, actually a very stable molecule, which leaves the system. And it produces the naphthalene ring system. So now we have two benzene rings. So we created two benzene rings from none. And this is a very thermodynamically favorable process. It's also favored in an entropy sense since it expels carbon dioxide as well. All right, yeah, so I actually had several more problems, though didn't realize how long this was. Okay, here's one last one that's going to introduce us to the resonance stabilization and how it differs when you have substituents in the ortho versus para versus meta system. Which carbocation is more stable? Carbocation on the left, which we'll call A, or carbocation on the right, which we'll call B. All right, to answer this, what we start doing is we want to draw all of the resonance forms we can draw here. Okay, so the one on the right, carbocation B, is more stable due to resonance. All right, so in the top here we have resonance forms for A, and what you see when you look at these is that we have the resonance forms you'd expect to write, where we have it in the ortho position, the para position, and the other ortho position. But when you do the same thing for the paramethyl group right here, these resonance structures lead to one uniquely stable alternative resonance form. This one, where not only is it doubly allylic, but it's also tertiary. So the fact that you can write this one resonance form where the methyl stabilizes the carbocation also directly means that this is going to be the more stable carbocation. So we would pick B as being the more stable carbocation because the methyl is directly involved in the stabilization